So in this video we are going to prove that the dual of LP is LP prime. Now when I say this, it's not quite clear what I mean, because the dual of LP is a space of continuous linear maps from LP to the real numbers, whereas LP prime is a space of P prime integrable functions, or more precisely equivalence classes of functions up to the almost everywhere equality equivalence relation. So let's make that a little bit more precise. So what do we mean? Meaning that LP star is going to be the set of all maps of the form LG going from LP to R, running over all G in LP prime, where LG is the map that sends a element of LPF to the integral of F times G. And so we're going to prove that. We're going to prove that all of the dual of LP is only made of linear functionals of this particular form, an integral of F times G, as we would know from the rest representation theorem, if P were to be equal to 2. And not only that, but also the norm of these functionals would be precisely the norm, the LP prime norm of the function. So it's an identification between the dual of LP and LP prime, and the identification is by identifying a linear functional with the element of LP prime that it has to come from, because all of the linear functionals will have to be of this form. Okay, so there's two steps. First of all, we need to show that things of these forms are indeed linear functionals, and that their LP star norm is exactly the LP prime norm of G. And on the other hand, we need to show that every linear functional in LP star is of this form, which is going to be the hardest part. Okay, so to prove the hard part of the theorem and prove that the dual of LP is LP prime, we're going to have to study the functional in LP star and show that they are of the specific form of an integral against a function in LP prime. Now, to do that, it would be very convenient to first restrict our attention to what's called a positive functional. And the lemma 6.6 here that we're going to prove first is going to allow us to do that. So what's a positive functional? It's a element of LP star that sends positive elements to non-negative real numbers. So what's a positive element? A positive element of LP is a element of LP which for almost every x takes non-negative values. So whenever you have a function in LP, you could always write it as the difference of two positive elements, right? You take the maximum of the function and 0, that gives you a positive element, and then you can take the function minus that, and that would be another positive element that you subtract. Now, in exactly the same way, when you have a functional in LP star, you can decompose it as the difference of two positive functional. Now, it's a little harder because you cannot just take the maximum of the value in 0, because if you do that, it's not going to be a linear operation. You have to stay linear, right? L plus and L minus are going to be both elements in LP star. So the first thing we need to see is how you do that, how you decompose general functional as the difference of two positive functionals. And then in the proof of our theorem, we'll be able to restrict our attentions to positive functional. And that's going to be helpful because we're going to be constructing a measure, and measure in general take non-negative values. So let's see the proof of this lemma 6.6. Okay, so let's give ourselves an element L in the dual of LP, an element F in LP. If F is positive, then I'm going to define L bar of F as the supremum of all those L of G when G is anything below F. So an element of LP that is positive and below F. And what I mean by this sort of inequalities between function, of course, is this holds g of x is less or equal than f of x for almost every x, and g of x is non-negative for almost every x. All right, so I'm defining an element in that way, and if f is not positive, or in general, let us define its positive and negative part. So I'm going to define f plus of x as the maximum of f of x and 0, which of course is greater or equal than 0 for every x in R. And I'm going to define f minus of x as f plus of x minus f of x, which is also greater or equal to 0 for every x in R. And f can be written, because of this equality, of course, f can be written as f plus minus f minus. And then I'm going to define L plus of a general f for all f in LP as L bar of f plus minus L bar of f minus. Right, so that's my candidate for being the L plus part, and of course I'm going to define L minus of f as L plus of f minus L of f. Right, so what do we need to show in all of this? So we need to show that L plus and L minus are in LP stars. First of all, we need to show they are linear functionals, and we need to show that they are positive. All right, now maybe let's start with the positivity, and then we'll work on some of the hard part, which is the linearity of these maps. Now, of course, I'm only going to need to really show the linearity of L plus, and then by definition of L minus, the linearity of L minus will follow. But let's check the positivity first. So what happens if I take L plus of f plus, right? If f is positive, then f is equal to f plus, and then I get by definition that it is L bar of f plus. And what can I say about L bar of f plus? Well, it's certainly greater or equal than L of 0, because it's the supremum of the L of g's over all g, and I could take g constantly equal to 0, and L of 0 is 0 by linearity. So L plus is certainly positive. Cool. What about L minus? Well, to prove that L minus is positive, let's have a look at L minus of f plus. It is L bar of f plus minus L of f, and I need to show that, minus L of f plus, and I need to show that this is non-negative. But L bar of f plus, I mean f plus is a element that is less or equal than f plus, of course. So this, because L bar is defined as a sup, this is smaller than L of f plus minus L of f plus, which is 0. So L minus is positive also. Right, so I have my decomposition of L into the difference of two positive maps, L plus and L minus, maps that sends positive elements of LP to non-negative reals. But what I need to show now is that L plus is continuous. So this is the next bit, continuous and an element of LP star. And then the rest will follow. So it remains to show that L plus belongs to LP star. Let's do that. Okay, let's start with the linearity. So let's give ourselves two elements, f and h, and then maybe in a step 1, I'm going to assume that they are positive. Okay, now I want to compute L plus of f plus h. So let's take elements, let's call them G1 and G2, such that G1 is between 0 and f, and G2 is between 0 and h. Okay, then what can I say? Then G1 plus G2 is going to be non-negative and below f plus h. So when I take L plus of f plus h, this is L bar, first of all, of f plus h, because f plus h is positive, and this is defined as a supremum, so it's certainly greater than L of G1 plus G2, which is just one element of the set over which I'm taking a supremum. And now L is linear, so this is L of G1 plus L of G2. Now the choice of G1 and G2 in LP was completely arbitrary, so I can take a supremum over all the G1 satisfying this and all the G2 satisfying there, and I get that L plus of f plus h is greater or equal than L bar of f plus L bar of h. But what is that? This is exactly L plus of f and L plus of h. So I have half of the equality that I need for linearity of L plus, at least restricted to positive elements. And then we'll get to more general elements by taking difference of positive elements. Now I also need the opposite inequality. So this is a little harder. So for that, I'm gonna give myself an epsilon worth of room, and I'm gonna consider a g between my 0 and my f plus h. Okay, and then I have to look at L plus of f plus h. Okay, and I'm gonna pick my g such that, you know, this L of g almost realizes the supremum. So L plus of f plus h is L bar of f plus h, and I'm going to choose my g such that L bar of f plus h is smaller than L of g plus epsilon, right? I take a g that almost realizes the supremum. Now I want to define, and let's call that g1 now, as the minimum of g and f. Right, so the point of such a g1 is that now obviously it is below f because it's the minimum, and g minus g1 is below h. So g1 is below f, sure. And then if I do g minus g1, this is smaller. First of all, this is greater or equal to 0 because I'm subtracting from g something that is smaller than g, because it's the minimum of g and f. But in the meantime, it is smaller than h, right? Because g being the minimum, yeah, because g is smaller than f plus h, and so it's also smaller than h plus the minimum of g and f, because h is non-negative, so g is smaller than itself and it's smaller than f plus h. Right, so now the point of that is that I have g that I can write as g1 plus g minus g1, and g1 is below f and g minus g1 is below h. So when I look at my L plus of f plus h, which is L bar of f plus h by positivity, this is smaller than L of g plus epsilon, which is equal to L of g1 plus L of g minus g1 plus epsilon. And now I can take a supremum, the L of g1 certainly is smaller than the supremum over all g1s between 0 and f. So this is smaller than L bar of f, and this second term is smaller than L bar of h, which is L plus of f plus L plus of h plus epsilon. So we have shown that L plus f plus L plus h is smaller or equal than L plus of f plus h, which is smaller or equal than L plus of f plus L plus of h plus epsilon for every epsilon. And thus we have the linearity of L plus, not quite linearity, but it's a group homomorphism, property for all f and h in LP such that f is f plus and h is h plus. Okay, so let's get to general f and h for from that result on positive elements. So let's F and H be in LP, general ones. And notice that, okay, if I look at F plus H, I can write it as F plus minus F minus plus H plus minus H minus. It's the decomposition, well, it's the definition of this F plus and this F minus. And of course, I can also write it as F plus H plus minus F plus H minus. So this tells me what? This tells me that F plus H plus, let's rewrite that properly. So plus F minus plus H minus has to be equal to whatever I've got on the other side, which is F plus H minus. Sorry, my minus should be down the way we've written things. Very good. F plus H minus, that's this term, plus F plus H plus. Right. So now these are all positive elements. I could apply L bar to that, and I get that L bar of F plus H plus, okay, plus L bar of F minus plus H minus is equal to L bar of F plus H minus plus L bar of F plus L bar of H plus. I'm using the linearity that I got in step 1. I should have called that step 2, I suppose. Okay, and so going even further, so what have we got? We've got that L plus of F plus H. So what is L plus of F plus H? L plus of F plus H is L bar of F plus H plus minus L bar of F plus H minus, and so this has to be equal to L bar of F plus L bar of H plus minus L bar of F minus L bar of H minus by the equality above, but that is exactly equal to L plus of F minus L plus of H by definition, plus L plus F plus of H by definition of L plus. Okay, so what have we got here? We've got that L plus of F plus H is L plus of F plus L plus of H for every F and H in LP. Okay, then we have to show, and I'm going to leave that as an exercise, that L plus of lambda F is equal to lambda L plus of F for all lambda in R, and the hint is do lambda positive first, right, and then realize what happens when you multiply by -1. So I'm going to let you do that, and then that's going to finish the proof of linearity, and then you have to do continuity. And why do we have continuity? Because if I look at L plus of F, well, this is L bar of F plus, this is smaller than L bar of L plus L bar of F minus. And what can I say about L bar of F plus, right? It's the supremum of the LG for G between 0 and F. So it's the supremum, certainly smaller than the supremum of norm of L in LP star times norm of G in LP over all those G's that are below F and below F plus, sorry, and non-negative, plus the supremum again of norm of L in LP star times norm of G in LP, this time for G between 0 and F minus. Right, now when you have non-negative function, if you increase the non-negative function, you increase its LP norm. So what I have here is smaller than norm of L in LP star times the norm of F plus in LP plus the norm of G, the norm of F minus in LP. Yeah, right, but F plus is below F and non-negative, and F minus is below F and non-negative. So these things are certainly smaller than 2 times the norm of L in LP star times the norm of F in LP. And therefore, we have that L plus is an element of the dual of LP. And then so is L minus because of the definition of L minus, and we've finished the proof of lemma 6.6. Very good. So having done that, we can now go back and prove the theorem that tells us that the dual of LP is LP prime at least when P is between 1 and infinity. We won't do the case P equal 1 in this course, but it works in a very similar way. Let's have a look. So step 1. Okay, in step 1, we're going to prove that LG is in LP star and the norm of LG in LP star is exactly the norm of G in LP prime. That's for every G in LP prime. So let's see that. Now, first of all, LG of F for any F in LP, what is that? In absolute value, it's certainly smaller, string inequality, than the integral of the absolute value of FG. And so by Hölder, we know that this is smaller than the LP norm of F times the LP prime norm of G. So you can take a supremum of all F that have LP norm equal to 1, and you get that the norm of LG as a element of the dual is smaller than the norm of G in LP prime. And of course, LG is linear as a function of F. LG of F is linear as a function of F. That's obvious because integrals are linear. So that is almost step 1, except I also need an inequality going in the other direction. So to do that, given a G in LP prime, as we have here, I'm going to define an F by f of x equal sine of g of x times g of x to the power p prime minus 1 divided by the LP prime norm of g raised to the power p prime minus 1. And by sine of x, I mean the function, which is 1 whenever g of x is non-negative, and minus 1 when g of x happens to be negative. Okay, so that f that I've just defined, I want to show that it is in LP. It has LP norm 1, and then I'm going to show that LG of f exactly is equal in absolute value as is the LP prime norm of g. So let's do that. So first of all, the LP norm of f, now what is that? Let's raise that to the p. This is going to be equal to g of x raised to the power p prime minus 1 times p divided by the norm of g in p prime raised to the power p prime minus 1 times p. But what is p prime minus 1 times p? I mean, p is p prime divided by p prime minus 1. So this is exactly the norm of g in LP prime raised to the power p prime and divided by the norm of g in LP prime, well, raised to the power p prime. So this is 1. And when I look at LG of f, what do I get? Well, I get the integral of sine of g of x times g of x, which is absolute value of g of x times g of x to the p prime minus 1 divided by the norm of g in p prime raised to the power p prime minus 1. And what is that? Well, it is the LP prime norm of g raised to the power p prime divided by the LP prime norm of g raised to the power p prime minus 1, which is the LP prime norm of g. So what do I get? I get that the LP prime norm of g is certainly smaller than the supremum of all LGF when f has norm 1, because it's equal to LGF for a specific choice of f that has norm 1. Okay, and that concludes step 1 of the proof. Now we're going to move to step 2 and shows that every linear functional in LP star has to be of this particular form L little g L subscript g for a g in LP prime. Okay, so step 2. Now we need to show that every linear functional in LP star, so let's take 1, is of the form LG for some g in LP prime. Now by the lemma that we've proven just before this, without loss of generality, I can assume that L is positive, right? Because if it is not, I decompose it into a positive part minus a negative part, and I prove this representation for both the positive parts and the negative parts. There'll be some LG plus and LG minus, and then I construct my G as G plus minus G minus. So, okay, so I can assume that L is positive. Now, what I'm going to do is I'm going to define a measure in this way. I'm going to define nu of E as L applied to the indicator function of E, right, for E a Borel set. Right, that's the idea. However, that's not going to work straight off the bat like that. I need to be in a bounded set to make this work. So I'm going to intersect that with the ball centered at the origin with radius n for some n, a natural number. And eventually we'll send that n to infinity. So right now we're going to restrict our attentions to functions which are supported in a ball of radius capital N, and eventually we'll need to send capital N to infinity. So I claim that nu n is a measure, and that is absolutely continuous with respect to the Lebesgue measure. Right. Now, if I can prove that, I'm going to then have the Rayleigh-Nikodym differentiation theorem kicking in, and my measure will be integration against the function, and that function will be the element of LP prime I'm looking for, at least restricted to the ball 0n, and then we'll send capital N to infinity. That's the idea here about how you construct the G. First you construct a measure, and then you apply Rayleigh-Nikodym differentiation. So let's, in order to prove that claim, let's first remark one continuity property that's going to give us the absolute continuity, and that's going to also be helpful in proving that nu n is indeed a measure. So, well, I mean, because my L is positive, nu n of E is a non-negative number. So that's a part of being a measure. It's going to be a bounded measure because I've restricted to this interval, to the ball of radius n, and I have that nu n of E is certainly smaller than the LP star norm of L times the LP norm of this indicator function. Right, but what is the LP norm of this indicator function? It is the Lebesgue measure of this set. I'm going to use absolute value to denote Lebesgue measure in this proof, raised to the power 1 upon p. So, of course, if the set had measure 0, so we're going to use that, and I'm going to call that 1. But in particular, if the Lebesgue measure of the set is 0, then nu n is certainly 0. And that gives me the absolute continuity of the measure with respect to the Lebesgue measure, as long as nu n is a measure. So let's check that. So in order to check that, I have to look at sets, Borel sets E that are union of disjoint sets. En disjoint Borel set. Right, and why do I need to show? I need to show that nu n of E really is the sum of the nu n of E little n. Okay, so how do we do this? So first of all, we show that if I give myself an m in n, the sum from n equals 0 to little m of nu n of e. So I'm going to show one inequality. So what can I say about this? This is L of the indicator function. Well, this is L of a sum of indicator function by linearity of L. So the indicator functions of En intersected with the ball, 0 capital N. And then what is the sum of indicator functions becomes the En are disjoint. This is L of the union of these sets. Right, by disjointness and properties of indicator functions. And now this is equal to nu n of E of the infinite union minus L of the indicator function of the union for n going from n plus 1 to infinity. Now, whatever that thing might be, it's non-negative because L is a positive linear functional. So this thing here has to be smaller than nu n of v. So that gives me, and that's for every m, so that gives me one inequality in that equality I need to prove, ascending little m to infinity. But I need to prove an equality, so really what I would need is to show that this part here does tend to 0 as m goes to infinity. So let's see how we do that. So going the other way, we have nu n of v is certainly smaller than the sum n equals 0 to little m of the nu n of En by disjointness plus nu n of this union starting at m plus 1. But now, okay, now I can use the absolute continuity property, so property 1, and I can say from property 1 that this is smaller than the sum from n equals 0 to m of nu n of En plus the norm of L in LP star times the Lebesgue measure of this union. Raised to the power 1 upon p. But the Lebesgue measure is a measure. So, and the ENs are disjoint. So what I have here is really the sum from n equal m plus 1 to infinity of the Lebesgue measure of E little n intersected with the ball B0n. And all of that raised to the power 1 upon p. Okay, but this sum here has to converge because the En are disjoint, and this is a series of positive or non-negative numbers that is uniformly bounded. It's uniformly bounded by the Lebesgue measure of B of 0n, right? That's certainly smaller. The Lebesgue measure of B of 0n. And therefore the series is to converge. So when you send m to infinity, then you get that this tends to this sum here. Right, so that concludes the claim, the proof of the claim. Nu n is indeed a measure, and it's absolutely continuous with respect to the Lebesgue measure. Oh, by the way, I'm in one dimension, so this volume of the ball is really just 2n, and by the ball I mean the interval minus n to n, of course. It would work exactly the same way in higher dimension, obviously, it's just a different factor. Right, but that was the point of restricting to a bounded set in the first place to ensure convergence of the series here. So we have a measure, and it is absolutely continuous with respect to Lebesgue measure. Therefore, by the Radon-Nikodym differentiation theorem, okay, what does that give us? that means that, okay, for every n, there exists a gn, which is going to be in L1 of R, and such that for every E, a Borel set, let's call sigma the Borel sigma algebra. Actually, traditionally we call it, we use a cal B like that for the Borel sigma algebra. Nu n of E is the integral over E of Gn. Okay, so we have a family of functions Gn. They're in L1. We're going to have to check that they are in LP prime. But more importantly, we'd like to have just a single G in LP prime that would represent our measures. And the reason we are going to get that is the following. Notice that if E, that's a little remark, if E is included in a ball, let's say of radius capital M for some integer m, then what have we got? We've got that for every n greater or equal to m, nu n of E is going to be the same as nu m of E, right? That's because they all define as L of the indicator function of E intersected with the ball, and the intersection of E with the ball B0m or the ball B0n is going to be the same thing. So what have we learned from that? We've learned from that if x is in B0m, then Gn of x is Gm of x for all n greater or equal to m. Right, so this sequence of functions Gn for any point x eventually stabilizes. So we can define g of x equal the limit as n goes to infinity of the Gn of x for every x in R, right? This will exist for any x because any x is included in the ball of center 0 and radius to absolute value of x, say. Right, so this is my gx, and what have we got? We've got that nu n of E is the integral over E of G for every E included in the ball of radius n. Now, if that's true for this, by the way, this is equal to the integral of the indicator function of E times G. So you can take linear combination of that, and for a simple function of the form sum of ck indicator of ek, k between 0 and some number, I better not call it capital N, let's call it capital K, with ck's being some numbers, and ek being Borel sets, to the capital K plus 1. Alright, it's a bit of notation. So some Borel sets that are all included in a certain ball. We have that we have that the integral, we have that L, sorry, of f, because it's a linear combination of indicator function, it's going to be the sum of the ck nu of ek, which is the same thing as the integral of f times g, k equals 0 to capital K. So our LF is really an L little g, at least for simple functions that are included in a bounded set. So this LG that we have here now is a linear map, and we have that LG of f is certainly smaller than the norm of L as an element of LP star times the norm of f in LP for all f in LP that is a simple function supported, compactly supported in some ball. Right, but the set of compactly supported simple function is dense in LP. So by density, LG has a unique extension to an element of LP star, right? Extension by continuity of linear maps that satisfy such a continuity inequality on a dense subspace. So it has a unique extension, and therefore LG belongs to LP star and is equal to L. And if LG belongs to LP star, then by step 1, LG, its norm in LP star, has to be equal to the LP prime norm of G. And in particular, G has to be in LP prime. And that concludes the proof.